Hi, my name is Tachapon Saranurak. I will talk about expander decomposition. So just to give you a small an informal definition first, expander decomposition is a problem where you are given a graph and then you need to output a partition of nodes into cluster Vi, and you want that for each Vi it should induce an expander. By expander, it means roughly that the graph is well connected. This I will define further. At the same time, you need that the number of intercluster edges should be small. So all edges that cross each part shouldn't be too many. Okay. So this is introduced first by Cannon, Bambala, and Vetta, and there are many citations from the practice side. But I would like to tell you that there are actually many applications in theory. The first class of application is from approximation algorithm. So it is used to get approximation algorithm for unique game problem, all or nothing flow, node or edge disjoint path problem. And there are a newer class of application which is in the field of fast algorithm. Here, the first application is introduced by Spielman and Teng. They use this decomposition to get their first near linear time Laplacian solver. And then there are many more applications in the same flavor. Get near linear time for many problems like approximate max flow, for example. Also, not only in a static setting. More recently, we used expander decomposition to get a speed up for one of the very well studied dynamic problem, which is minimum spanning tree. To maintain a minimum spanning tree when the graph change over time. Okay. So the previous best update time was square root n for a long time. Then we use it, and then we use expander decomposition, and then we get very fast speed up to n to the little of 1. And also in this talk, Julia just give another application to shortest path on the problem of shortest path. Yeah. So here she get a fast speed up on a dense graph, very fast speed up on dense graph. Previously there was some algorithm with almost the same time, but that algorithm cannot return a path, although it is about shortest path. It can only return a distance. So very interesting how expander can be used for a distance problem. And actually there are many other applications in dynamic graph algorithm that I'm exploring, and actually it should be published soon. Also, in the distributed algorithms in conjugate model, expander decomposition is useful as well. This is even more recent. So just in this soda, people use it to get an improvement for triangle listing or enumeration, and then we improve it further to get like n to the 1/3. This is also tight. So also for exact edge connectivity, we get also like the first sublinear time algorithm on the distributed setting. So you can see that there are many applications, and today's talk is we will try to see how to compute expander decomposition very fast. So let's see the more formal statement and the history of how people have tried to compute it fast. So the first definition, phi expander. So consider the set A in the graph. I say that this set A is a phi expander. If you look at any cut, if you look at any subset S inside A, then the number of edges that go across S to A minus S compared to the total, the sum of the degree of the node in S, this is large. This is larger by like a fraction of by a factor of phi. Okay, so it means that look at any cut, a lot of edges must go across S to A minus S. And then the one which is kind of just the opposite of the next definition is just the opposite. So this is phi sparse cut. So we say that this cut S is sparse if the number of edges here is relatively small compared to the volume. Okay, so this is just, so you can see just by definition that A is a phi expander if and only if A does not contain phi sparse cut. Okay, so now what we want to get is epsilon phi expander decomposition, where each cluster is a phi expander, and at the same time there is only epsilon fraction of edges which is in the cluster edges. So given that we know the formal definition, let's see how to compute it. The first trivial algorithm is just the following. We just either certify that the whole graph is a phi expander. Otherwise, if it's not, then you find some phi sparse cut S, you cut it and you recurse on the both sides of S. Okay, you cut this thing and you recurse on both sides. So this recursion, when it stops, it will basically induce a partition of a graph. And we know that each part that the recursion stops must be a phi expander just by definition of the algorithm. What we really need to prove is only that the number of edges crossing each part is at most phi log m times m. But this is true because every time you find a phi sparse cut S, right, you cut it, and then you get a new intercluster edges which is at most phi volume as many. So you charge these new edges to the edges inside the smaller side of a cut, which are volume as many. So these edges that you charge is like phi fraction less than the edge inside. Now the edge can be on the smaller side by at most log n times. So just by here you get that each edge is charged by at most phi log m. So in total there can be phi log m times m intercluster edges. However, you can see that this is NP hard, but this is no problem. To get a polynomial time algorithm, we can just relax this algorithm a bit. That is, we either certify that a graph is a phi expander, or you find almost phi sparse cut. Right? This O tilde means polylog factor. And the analysis just go the same. you get some slack here in the number of intercluster edges, but you get polynomial time. Okay, however, this will still be slow. It will not be near linear time. Why? Because consider the following case: when you get a very unbalanced cut, you get S1, you cut it, then you recurse on the larger side, you cut another small cut, and so on. So the recursion depth here will be like can be at least omega of n, and this will give you a quadratic time. So what we want here is we want some balance guarantee. That is, so let me give one definition. A cut is the cut is balanced if both sides of a cut, the volume of both sides of the cut is quite large. It's larger than 1 over polylog fraction of the whole thing. Okay. So now the goal. Let me state the goal which is sufficient for our purpose. We want a near linear time algorithm that either do one of the following thing. First, it certifies that the whole graph is a phi expander, or it finds a balanced sparse cut, or it finds unbalanced sparse cut, but at the same time it certifies that the larger side of the cut is already a phi expander. Okay. So once we have this, we are done. It is quite easy to see. So look at this recursion tree. You kind of recurse on both sides. If it is a case 2, it is balanced. Here you recurse again on both sides because it is balanced. If it is here, this case, the cut is unbalanced, you only recurse on the smaller side. Okay, so you can see, because of this, you can see that the depth of this recursion tree must be small, because in the balanced case, it creates at most a polylog depth in the recursion. And in the unbalanced case, because we only recurse on the smaller side, so this creates only like log n recursion depth. And if we look at each level in the recursion depth, in the tree, then the total cost on each recursion level is also at most near linear, because our algorithm is near linear. So this approach is indeed used before, and this is actually used by Weizmann and Teng, but they actually relax this goal a bit in the following way. They say that, okay, the balance cut is getting worse by a quadratic factor, and more importantly, the larger side, when you get an unbalanced cut, they only say that the larger side of a cut is only contained in some unknown expander. Okay, it's not exactly expander, it is contained in some expander. So once we have this, can just do the same, just recurse in the same way as before. What we get is the near linear time algorithm to compute the decomposition, but we only get that each cluster is contained in some expander. So this does not induce expander, and because of this exactly, that is why some application cannot use it. There are some other work which improve upon Weizmann and Teng. They remove like a log factor here and there, and in the time and the epsilon, but still they cannot guarantee that like it does not induce an expander on each cluster, which is why they actually ask is it possible, they ask as an open question, is it possible to be fast and still each cluster should induce an expander? Is this possible? So this question is answered affirmatively by Danupon and me. So we managed to get this that the graph induce, that each cluster induce expander, but we pay the subpolynomial factor in our running time. Our algorithm is actually a black box reduction from expanded decomposition to a nearly most balanced 5-sparse cut problem, and we use a big hammer like approximate max flow. So because of this subpolynomial factor and the usage of big hammer that have a huge polylog factors in its running time, it motivates the paper in this talk. So we basically shave this subpolynomial factor out, and our running time is the first near linear time algorithm that such that each cluster induce expander when phi is at least 1 over polylog, which is the case for most of the application that use expanded decomposition. And our algorithm is actually simple and use only basic technique. So I really think that it is implementable. So this is a joint work with Di Wang from Georgia Tech. So just to mention some application, just directly by our statement, just plug in our thing into the old application. We managed to simplify, then it will immediately simplify the analysis and the algorithm of many previous work, and also shave some log factors. And also for some application, we improve the subpolynomial factor a bit. Okay. So let's see how do we do this. So the high-level overview is this. Look at this goal, right? The important case is when the graph is, the cut that we get is unbalanced. So the first step is to get this kind of the same algorithm as the goal that we want, but we only guarantee that the largest side of a cut is something called phi near expander. And then the second step is to, given this phi near expander, we can compute A prime, which is obtained by removing some part of a near expander, and show that this A prime is an expander, and the part that we remove is very small. To look at the picture, we have something like this. If we get case in the first step, if we get case 1 or 2, we are good. If we get case 3, we have that the largest side is a near expander, and then we will just trim some part of A and say that A prime is an expander. So this is the roadmap that we want. So to understand this, I need to define you what is a near expander. So let's look. Let me remind you an expander. So the near expander is just the same thing as the expander, except that when we count the number of edges, instead of counting the number of edges from S to A minus S, we count the number of edges from S to V minus S. So we also count the edges from S to outside to the thing outside A as well. Okay. So now let's start with So in step 1, this is actually not our main contribution. The main contribution is on the step 2, but I would like to talk about it a bit because the technique, which is a cut matching game, is really cool, and I just would like to mention it to everyone. To understand cut matching game, let me start with some warm-up related question. Suppose you want to show that in the graph there is no small st cut. How do we do it? Just by Maxwell's cut theorem. It is enough to show that that you need to find large st flow. Okay. So now the cut matching game asks this: how can we show that there is no phi sparse cut? Right. This is a more complicated question because phi sparse cut is not only about some pair st, but this is about any cut over all the graph that should not be sparse. So it turns out that the answer is almost as simple as the previous question. We just need to find large st flow a few times. So let me be more a bit formal. Given a graph, what you need to do, what cut matching game that you says that you need to do is only that you just augment the graph in some randomized way. Then you find large st flow, and then just repeat this for a log square n times. You augment the graph, you find the flow, and repeat this. Okay? If you can do this, then in some certain way in the augmented graph, okay, then you certify that the graph is a phi expander. And given that given this thing, and given that and actually there is another algorithm that such that it will return a sparse cut whenever we cannot find a large st flow in any round in this game. To get this together, you will get the following algorithm, which is a near-linear time algorithm that either certify that the whole graph is a phi expander, or you get some phi sparse cut. Why? Because in the first case, if we get large st flow in overall rounds, we get the first case. Otherwise, by the second algorithm, we will get a sparse cut. We just stop the game and we return that cut and we are done. Okay. However, this algorithm does not have any balance guarantee. So our modification of cut matching game is simple. The idea is just the following. Whenever you find a sparse cut in any round, you just continue the process. You don't stop, you continue the process on the remaining part of the graph. That is, here you augment the graph, you find the flow, and you also get some sparse cut. You just cut it and continue on v minus s1, and you repeat this for log square round. So at the end you get some graph. So let me denote S star by all the part that you remove throughout each round. So S star is also a phi sparse cut, almost phi sparse cut. Why? Because the union of almost phi sparse cut is a almost phi sparse cut as well. This is easy to see. And now, given this thing, I claim that we are done with the step 1. Why? Because if S star is empty, then you get an expander. Otherwise, if S star together is big, you get a second case. If S star is unbalanced, then I claim we show that the larger side is the near expander. This is done by just looking at the analysis of a card matching game. So now we have step 1. Let's go to step 2. Okay, before going we need to look at some background. We need some knowledge about. I need to tell you some background knowledge. Let's start with the first observation. So suppose that you have that A is a near you have this A which is an expander, right? But suppose it is not already expander. Then I claim that there must exist a set S, right? Such that the number of edges going from S to A minus S is much less than edges from S to R. Why? Because you know that A is not an expander, so there must exist a set S that certifies that a sparse cut. But because A is a near expander, so although there are few edges here, S have a lot of edges going out from it. Now use a simple math. You will get this inequality. So the next thing that I need to define is the flow problem with respect to A. This will be used throughout the talk, so this is important. So given A, I define a graph in this way. I connect the source to all cut edges from R to A. The capacity is 2/5, and each edge have capacity 2/5 in A, and each node I have the edge to the supersink. The capacity is degree. So let's see. We claim, and now I claim that if the max flow value is exactly is like 2/5 times the number of edges here, that is, each cut edge can send a flow at its full capacity into A. Okay, then A will be like a 5/6 expander. And to see this is simple. Just assume otherwise, that A is not a 5/6 expander. By the claim that we just saw, we know that there must exist a set S such that the red edge are much fewer than a green edge incident to S, right? And by here, we will just show that the flow that goes into S will be larger than flow that go out of S. So the flow must get stuck somehow, and because of this, max flow must be less than what we claim, and this is a contradiction. So to see this quickly, look at this. A flow going into S is at least 2/5 times the green edges here, which is at least this. And flow going out of S is at most the total volume of S, which is why, because recall that each node connects to the sink with degree capacity. And also we have the red edges here. Each of them have capacity 2/5. So now important thing to note is that because A is a near expander, right? So we know that the total number, the edges that go out of S, green and red, compared to the volume is quite large. Okay, so we have this. Now just use a simple math, and we get the claim, and we're done. So now we will use this claim, okay, to get our algorithm now. That is, so do it, but we will actually get like a warm-up version actually. So consider this problem. Given this flow problem, I just compute an exact mean cut S and also the max flow, and then I claim that just by removing this S from A, we get an expander. And note that if S is just S0, the sink, then A itself is an expander. Why? This is important. So if you look at when you compute exact max flow, right? If you look at the mean cut, each edge crossing the mean cut will have flow at its full capacity. Okay, you have that every edge crossing the mean cut have full capacity flow. But once we have this, let's look at the problem where we just remove S and we get the flow problem with respect to A prime. Okay, so now just by reusing the flow that we compute for the problem with respect to A, we get a flow with respect to A prime that have size exactly 2/5 times the number of cut edges. So this immediately gives us just by applying the claim that we use, that we claim, but this is a claim for A prime instead, then we get that A prime will be an expander. So we are done, right? We get that A prime is an expander, but not only that, we have something more. We can show that also the volume of S will be small, and the size of the cut, the new cut from A to outside A, is like almost is the same. It's not more than before. Why this is true? This is just because S is a mean cut. So and the size, the cut value of S is this much. The cut value of S0 is this much. You compare the two terms and you get this thing. So that is, we have also that S will be small, and the size of the cut of the new cut is not larger than before. So this is good. This is exactly what we want, but it is slow. So now it's time to tell you how to get it fast. This is the last part. So the main goal of this part is to give you only like a high level remark roughly how you can get really fast algorithm. And actually what we get is the time of the algorithm does not even depends on the size of the graph. Okay, it's a local time. So to see this, we can need to see that exactly why it was slow is because we use exact max flow, right? But this is really good for us because once we use exact max flow, we know that each cut edges will have flow at full capacity across the cut. But to get it fast, we need to use approximate max flow instead. But because of this, we will get a relaxed guarantee. That is, we have only that most cut edges have flow that almost full capacity across the cut. There can be some edges, only few of them though, that are like far from being full and maybe like going in even the wrong direction. Okay. How do we get? So let me define an algorithm that the framework of the algorithm that we will use. It is not fast yet, but let's see. So we will repeatedly do the following. We first compute approximate mean cut S in the flow problem with respect to A. And then we just, if it turns out that not almost all, but all cut edges have almost full flow to S minus A minus S. Using the same kind of argument, you get that A minus S is also like now will be like an expander with some quality here, which is worse than 6, but which is worse than 5/6, but it's fine. If this is not the case, that there are still some edge with a wrong direction that have flow in the wrong direction or not almost full, then we just remove S from A and we repeat it. So the intuition why this might be good is this: we have that so many cut edge have a flow in the correct direction, so maybe we can reuse it, and there are only few of them that we need to fix, right? So the algorithm will go like this. Once we get the cut, some of them is wrong, but we just look at the next iteration. We connect the source. To every cut edge again, and then find the flow. Okay, so and find the approximate mean cut. Okay, sorry, and just repeat. We get some cut, and if we don't get case 2 yet, we just continue until we are done. Okay, so actually, if it turns out that we can bound the number of rounds in this algorithm, everything will be easy. At least we get a near linear time algorithm just by running approximate max flow in the undirected graph in each round. But however, we cannot bound this number. So now this is the key technique. How do we get everything fast? Our flow algorithm will do this. It will run, and although there are many rounds, we are able to show that the total running time over all these rounds will still be small. And the key idea is to reuse the flow and other information from previous round that we maintain. So this is kind of some like dynamic flow algorithm. We remove some cut, we reuse the flow that we maintain, recompute it again, and then we like edit the graph and we will continue. Okay, and the algorithm to implement this thing is, I call it a bounded height push level. And this is introduced by Hensinger, Rao, and Wang. And this is actually just a classic push level McFlow algorithm that is introduced by Goldberg and Tarjan, but with one modification, that is the height or level which is maintained in this push level algorithm, it will be bounded by something small instead of 2n as before in the classic algorithm. So once you bound this height, it will be much faster than the classic one, although it does not compute exact McFlow anymore. Okay, what is left is only like how to analyze this algorithm, that it really gives what we want. The why it is fast is just by looking at the analysis. But let me give you like a bit more like high level idea why at all this algorithm is a good one, although we don't need to go into how it works, because to do that I need to tell you how push level works, and we don't have time for that. So the first reason is this. This algorithm, bounded height push level, actually is the algorithm for computing approximate McFlow in directed graph. Okay, so this is important. We don't in general, but this works only because we are in our graph instance have each node, that in our graph instance each node have an edge from itself to the sink with capacity degree. Okay, so this algorithm compute approximate McFlow in directed graph in some special graph. For general graph, this is a big open problem, but for this special graph, you can do it fast. And it is important that we work on directed graph. But why? Because we will reuse the flow, and by reusing the flow we need to work on the residual graph, and this residual graph is directed. Yeah. So this explains why at least this algorithm fit into the framework of computing approximate McFlow. Okay. And the next high level reason is this. The algorithm here, the analysis of this push level algorithm is by using some potential function, and this is very flexible for this dynamic setting where we compute the flow, we remove some part of the graph and recompute the flow again, right? This is on the dynamic graph. But this potential function is really useful because whenever we adjust the instance between each round, we cut something, we adjust the level a bit and so on, we can just analyze the running time affected by this operation just by computing the potential change, and this is very convenient. So just by this together, the final algorithm is just we compute approximate mean cut using this algorithm, bounded height push level, and this algorithm will reuse the flow from previous rounds, and we keep doing this, and with some analysis we basically get what we want. The time follows by the argument, the high level argument that I tried to convince you before, and the other part of the other property just follows by kind of the same idea as before, as I proved to you in the when we use exact max flow in the slow algorithm. Okay, so now we are done. Our algorithm is by have two steps. The first step is by using a cut matching game, a variant of it, that we continue the game even after we find some sparse cut. The second step is about trimming. We use a classic algorithm in a new way in the dynamic graph. And this is why we get this two step here. This together give us our goal that we claim that suffice for getting the linear time algorithm. Because just to remind you, we get some reduction like this, some recursion like this, and by careful analysis, we get this polylog factor, this much polylog factor. And now to give you some open problem questions. First, how can you remove 1/5 factor from our running time? And the next one is whether you can parallelize or make distributed algorithm out of hours. There should be some more application on it. So thanks.